Hello again and welcome back to my physics class. This is Electromagnetic Lesson 2. And before we begin, let us revise a bit what have we discussed and learned in Lesson 1. In the first lesson on electromagnetism, we have learned how the permanent magnet and a current-carrying conductor such as straight wire, a coil or a solenoid produces magnetic field around them. And today we are going to look what will happen to this current carrying conductor as I place them in between these two magnetic fields. So can you guess what will happen to this current carrying conductor which I place in between of these two magnetic fields? To know the answer, let us begin this simple experiment. This blue line shows that the magnetic field in between these two permanent magnets where it is directed from the north heading to the south. And let us take a look what will happen as I switch on this button. Okay, you can see now there is a current flow in this current carrying conductor in this direction. And this is the pattern of the magnetic field around the current carrying conductor, which is a concentric circle as we learned earlier in Lesson 1. And at this side, you can see what happened. There is an interaction between the magnetic field of the current carrying conductor and the magnetic field of the permanent magnet. And this interaction produces a combination field which is called as a catapult field. So what will happen to our current carrying conductor now as this catapult field is produced? This catapult field will exert a force on the conductor and pushes it towards a region where the field is weaker. So how to know which field is weaker and which field is stronger? If you refer to this diagram, this is the direction of the magnetic field of the current carrying conductor, while these are the direction of the magnetic field from the permanent magnet. And at the upper region, we can see that when the field lines of the permanent magnet and the field lines of the current point in the opposite direction, they will cancel each other, resulting in a weaker field. And down here, when the direction of the two fields are the same, the field will merge and producing a stronger resultant field. So what will happen to our current carrying conductor? It will be pushed upward from the stronger region to a weaker region. And how to determine the direction of the force acting on the current carrying conductor, either upwards, downwards, to the left or to the right, it depends on the direction of the current and the magnetic field. Okay, now let's take a look at this experiment where we place a copper wire in between this magnetic field. And this copper wire is connected to the power supply using the connecting wire. And you may observe in which direction this copper wire will swing to, either inwards or outwards when I switch on this power supply. First, this is the direction of current flows through the copper wire, and you can see that the copper wire swing inwards. Now what happened when I change the direction of the current? See, when now the current flow in the opposite direction, the copper wire will swing outwards. Now, let us repeat the experiment and observe the formation of the catapult field as the current flowed in a two opposite directions. Initially, when current flow in this direction along the copper wire, this diagram shows how the catapult field are produced. On the right side, since the direction of the magnetic field of the permanent magnet is equal to the direction of the magnetic field of the copper wire, so it formed a stronger region. While on the left side, since the direction is opposite, so it produced a weaker region. And this caused the copper wire push to the left, which is inwards. And now when I change the direction of current flow in the copper wire, this diagram shows how the catapult field are produced. On the left side, since the direction of the magnetic field of the permanent magnet and the copper wire is the same, it produces a stronger region. While on the right side, since the direction is opposite, so it produced a weaker region. And as a result, the copper wire is now pushed to the right, which is outwards. So everyone, this is the rule which we apply behind all this. It is called as a Fleming left-hand rule, where the thumb indicates the direction of force acting on the current carrying conductor. The first finger represents the direction of the magnetic field, and the middle finger represents the direction of current along the wire. And this Fleming left-hand rule, it gives the relative direction of the force, magnetic field, and the current, which all of them are at the right angles to one and another. And to have a further understanding on how to apply this rule, let's take a look at this animation. You may observe the changes in direction of force acting on this wire when I change the direction of current flows through it. Okay, first, when current flow in this direction as shown by the red arrow, this is how the catapult field looks like. And you can see the force is now acting upwards, as shown by the Fleming's left-hand rule here. Alright? Okay, now let's change the direction of the current. So when the current flow in the opposite direction, this is the new catapult field which is produced, and now the force is acting downwards, as shown by the Fleming left-hand rule here. So by this example, I hope you have a clear understanding on how to apply Fleming's left-hand rule. Again, the thumb indicates the direction of force or motion act on the conductor. The first finger or the forefinger indicates the direction of the magnetic field, while the middle finger or the second finger indicates the direction of current along the conductor. So we have done with the Fleming's left-hand rule, and now let us take a look at the factor affect the magnitude of the force acting on a current carrying conductor placed in between a magnetic field. According to these two diagrams, there are two factors affect this magnitude of force. Factor number one is the magnitude of current, which determines the strength of the magnetic field produced by the conductor. And factor number two is the size or the strength of the magnet and the material, which determine the strength of the magnetic field produced by the permanent magnet. And to understand these two factors, let us take a look at this simple demonstration. These are the two factors affect the magnitude of force acting on the current carrying conductor, which is placed in between a magnetic field. And in each case, one of these factors will be kept constant. To begin, let us maintain the magnetic field by changing the magnitude of current and see what happened to the magnitude of force acting on this current carrying conductor. So now a small current flows through the conductor in this direction, and it shows that the conductor swings outwards at this angle. Now what happened to the angle of motion when I increase the magnitude of current flows? You can see that the angle of motion or the angle of swing is bigger. It shows that a bigger force is acting on this conductor. And now, as I said, the current at the maximum value, the angle of motion or the angle of swing keep increasing, and again shows that a bigger force acting on the conductor. And now to study the second factor, we keep the current constant. And again, you may observe on the angle of motion or angle of swing of the current carrying conductor as I change the strength of the magnetic field. Initially, when the magnetic field is weaker, the current carrying conductor swings at a small angle. And now, when I increase the strength of the magnetic field, for example, by using a bigger or a thicker magnet, you can see that the current carrying conductor swings at a bigger angle, showing that bigger forces acting on it. Okay, for the next activity, I want you to observe these two diagrams. The diagram on the left shows when the direction of the current and the magnetic field are parallel, the force experienced by the conductor is zero, means the conductor moves nowhere. While the diagram on the right shows that when the conductor and the magnetic field are not at the right angles, the force experienced by the conductor will be smaller than if they are at the right angles. Let's take a look at this application on how the moving coil loudspeaker make use of this magnetic force in producing sound. And these are the parts of this moving coil loudspeaker. We have a moving coil here, a permanent magnet, and a paper cone at this side. When the input signal flows through the loudspeaker, it will experience a varying force due to the magnetic field and start to vibrate. And this vibration will cause a cone attached to it also start to vibrate and finally produce sound. And now let us take a look on how the magnetic field of a two current carrying conductor interacts when they are placed nearby. In this diagram, you can see that the current carrying conductor and their respective magnetic field. And the ways of interaction between the magnetic field of a parallel conductors depends on the flow of current in both. Either current flows in the same or opposite directions. First, we set so that the current flows in both conductors are in the same direction. And you can see that the conductor is now pulled towards each other. And now what happens when we make the direction of current flow in the opposite direction? The two parallel conductors are now pushed apart from each other. And to explain the situation, let us take a look at this diagram. On the left, where the current in the parallel conductors flow in the same direction, the opposing field line at the center will cancel each other, producing a weaker magnetic field here. While at these two sides, the magnetic field are stronger and it will push both conductors inwards where they attract to each other. And by this, we can say that when the current flows in the same direction, it produces a force of attraction in between the two parallel conductors. While on the right side, where the current in the parallel conductors flow in the opposite direction, the field line with the same direction at the center merge and produce a stronger magnetic field at the center. While at these two edges, the magnetic fields are weaker, so both conductors will be pushed apart away from each other. So by this, we can say that when the current flows in the opposite direction, it produces a force of repulsion in between the two parallel conductors. So see you again in the next lesson. Till then, Assalamualaikum and thank you for watching.